You meant me.
Why about the name?
The one that. So if they hear you are.
It was live. That I need to copy it. That resume. I can close this now.
Yes.
King.
I'm trying. I know your. This now. I know your spot.
Okay, I didn't mention.
Adejumo.
One of the pins.
Hello. Good afternoon, everyone. I hope you people are ready for the class today.
Yes, sir, we are.
At least the lecturer is possible. I think we are ready now.
Good afternoon, sir.
Yes, we are ready, sir.
Yeah, no. I see the next question. Calculating. Yes. Okay. Over here. Okay. Did this. So we have to start from here. Huh? I have to boot everybody. On. Okay, good morning. I hope you can hear me. The time is 12:06. So we continue from where we stopped during the last lecture. During the last lecture, we discussed how you can calculate the E cell when you have electron left in your net equation. But I said that once there are no electrons left in the net equation, you can use the normal method. But once your net equation has an electron left, then that means you have to use the delta G method to calculate the E cell. And after that, we actually went back, we did some other things. So we look at Nernst equation, and we saw the various forms of net equations. If we are using natural logarithm or if you are using log to base 10. So we just continue from that example that we had last time. So now this is calculation of equilibrium constant from E naught cell. And so we already said that delta G naught is equals to minus NF E naught cell. All this we did during the last lesson. And we went on further to show you that for a standard condition, your E naught cell will actually be equals to 0.0592 over N log K. So this relationship makes it very easy for you to be able to calculate your equilibrium constant from your E naught cell and your E naught cell from your equilibrium constant. So we continue from here now, and we look at various examples. Now, the first question we have here is calculate the equilibrium constant at 25 degrees C for the reaction occurring in Daniel's cell. Well, Daniel's cell is this equation, as you can remember, and the E naught cell we have already calculated before. So we just bring that down because we know what the E naught cell is. So the E naught cell is 1.1. So what you have to do is to go back to that equation I gave you last, where E naught cell is said to be equal to 0.592 over N log K. So your log K now will be equals to N multiplied by E naught cell over 0.0592. So you just simply substitute in the various values, and your K in this case is 1.5 times 10 raised to power 37. So this is a method you can use to calculate your K from your E naught cell, and you can do it the other way too. Let's look at another example. So this other example is calculation of equilibrium constant for this reaction. You have been given this reaction, and the E naught for each of the reaction half cell reactions have been given here. Hydrogen plus going to hydrogen is 0. Ion 3 going to ion 2, that is equals to 0.771. But remember, your net equation is this. Is that okay? Look at your net equation. What you have on this side of the net equation is hydrogen gas, and here you have proton. So invariably, well, normally what you ought to do, you are going to change this one here and reverse it to the other side so that this one will be minus 0. But minus 0 is still 0. So we won't bother ourselves with that. If you solve that equation the way we have done now, then your net equation and your E naught cell is going to be 0.771 volts. So that is the E naught for that reaction. Then you now go ahead and substitute. But before then, if you look at this equation, how many electrons are involved? 2. You see, we have to nullify 2 electrons on both sides. So that means the number of electrons flowing is actually 2. So that means your N in this case is 2. And your E naught is E naught cell is 0.771. So you just go ahead and substitute into that equation. 0.771 equals to 0.0592 over 2 log K. And in that case, your K is equal to 1.14 times 10 raised to power 26. If you look at what you have here, this is mole square per dm cube. The unit is determined from the equilibrium constant. The equilibrium constant of this is, what is this? What you have here, the aqueous solution you have here, the aqueous here, and then what you have here. So ideally, this will be H, this will be what your H here, the concentration is squared, and your Fe2 plus here, the concentration is squared, over the concentration squared of the F3E3 plus. And that means what you'll be left with will just be one concentration raised to power 2. And that's why you have mole dm raised to power minus 6. So you consider the ionic species that you have here to determine that. And this is what we have. Look at it. So this unit here will cancel this unit. So that means what you are going to be left with is what you have here. And then your unit is this. And that is what we put in here. So we go on and look at another one. The equilibrium constant for this reaction. You have half plus this, giving 8 half hydrogen plus Fe3 plus, giving 8 plus Fe2 plus. If you look at this, you discover that you have the same species in the two reactions, except that in one case you have half hydrogen instead of hydrogen plus that you have, and here you have H2 plus 2Fe and plus 2Fe3 plus to give 2H plus F2Fe2 plus. So you go on and do similar thing to what we did earlier. You know, you turn this one the other way. Well, this is what you have here, but the net equation, you know what you have here is H2 plus. So just go ahead and calculate, and then you have your Fe3 plus electron giving Fe2 plus as you have in that equation. Now, if you get your final equation, the major problem here is that if you look at the net equation here, you only have one electron that is used. Is that okay? You have just one electron. If you have one electron and you decide to calculate here, you discover that the value of your K is going to be different from what you got earlier. The value of your K is 1.1 times 10 raised to power 13. And your unit here is mole per dm cube. Because if you look at this equation, you can just go ahead and do it, and you discover that what you are going to have is going to be mole per dm cube. So the number of electrons that are actually involved will go a long way to change the value of your K, and will also change the units that you are likely to have from it. So you have to be conscious of the equation that you actually use. So if you look at this, this is actually the square root of the earlier one that we did. So if you find the square root of this equation we got earlier, you discover that your K is just the square root of it. So there are various equilibrium constants that you can calculate from various cell potentials, but you have to be really very, very careful about the values that you are using. So there are other examples of equilibrium constant that you can calculate. Solubility product, for instance, complex formation equilibrium, for instance. There are various types of equilibrium constants. So we go ahead now, look at some of these examples. This is for solubility products. You have your silver plus 1 electron giving you this. And if you have your silver chloride plus 1 electron giving you silver solid plus chloride minus. And the if inner cell is normally given. So the equation for finding solubility product for silver chloride normally will be silver chloride to give silver plus chloride minus. This is the equation you are looking for. So you have to look for a way of how are you going to arrange this to get this product. And if you are looking for how to do that, that means your AGCL will have to be on this side, and that means this other equation has to be reversed. Is that okay? That's the first equation has to be reversed. And if you want to reverse that first equation, that means your AG S will be going to AG plus, and that means this value is going to be negative of what you have here initially. I hope you can see it. So this is going to be negative, and then you bring down the other equation. After bringing this down, then you can now find the net equation. If you look at the net equation now, your silver plus here will cancel the silver, and your silver solid here will cancel the silver solid here. So what you have left is this electron here will cancel electron here. Then you have your silver aqueous, silver plus aqueous, and chloride minus aqueous. And if you add this one together, just like you have done here, your E0 cell is equal to 0 minus 0.580 volts. Now, so that is the value of your E0 cell. So you have to now go ahead and substitute into that equation to determine your solubility product. And remember, this is your E0 cell is equal to RT ln K over NF. We've not been told what are the conditions. But if it's under a standard condition, that means you have to go ahead and apply the standard condition. Is that okay? So that means your E0 cell is minus 0.58. Your Faraday is here. Your temperature is standard, that is 298, and you have your gas constant. And therefore, your ln KSP, this is your special equilibrium constant now, solubility product. That is equal to minus 22, what you have there, minus 22.587. So you now have to find your KSP now will be e raised to power. So your KSP is now going to be e raised to power minus 22. Yes, you have it here. E raised to power minus 22.587. And that is the same thing as 1.55 times 10 raised to power minus 10. So from here, you can see now how you can use your E0 cell from your experiment to calculate the solubility product of any of the compounds that you have. You have done this now for sodium chloride. You can use it for other compounds that are sparingly soluble. That's the only condition where you can use solubility products. So let's go for another example. This example this time around is for the complex formation. For the complex formation, this is the complex, the half reactions that you have, and you are looking for the complex formation of zinc into ammonium 4, and then with your ammonium 4, then 2 plus. So what you do now is that how do you arrange this equation so that you eventually have this product formed? So if you are going to have this product formed, that means the first equation here has to turn the other way around. Is that okay? So if you turn the first equation the other way around, then your equation here is going to be this. You are going to have this one now as your equation, and you reverse just like I've said, and your oxidation reaction now, this one is going to turn this other way, and this is now going to be positive instead of minus that you have here before. And then the other part of it will come down the way it is. This is minus, and it remains as minus. And now you find the overall equation. If you now look at this very well, your zinc here will cancel the one here. So that means what you have left here is zinc 2 plus. You have 4NH3 gas. 2 electrons here will cancel 2 electrons there, and you have only this one left. So now your E0 cell is this value. So it's this value now that you have to substitute into that equation. Is that okay? But note that normally at equilibrium, your E cell is equal to 0. At equilibrium, your E cell is equal to 0. E cell is whatsoever you have when the condition is not standard. When the condition is standard, is what we have calculated now that we said E naught cell is equal to 0.277 volts. Now, so the next thing you have to do is to substitute in here and calculate your K formation. In K formation will be equal to minus, that will be NFE naught over RT. Then you substitute, then you get your link KF, and then you can find your KSP. This is not KSP, this will be K for the complex formation. It should be CF, not SP. So, and that will be E raised to power 21.575, and that value is 2.344 times 10 raised to power 9. So that's another example, and we can go on and on and on and on. But you see, what we have just done is when you look at standard conditions, in most of the cases we have checked. There are situations where what you have are not in standard condition, and that will lead us to what we call the popular Nernst equation. Nernst equation. So the equation here is going to show the relationship between the electropotentials and the concentration of the reactants. I said, well, it's named after Nernst. So let's look at the various standard conditions. If you have this, which we have been using all along, we say 1 molar, your popular Daniel cell here, your E naught cell, because it's under standard condition, E naught cell is 1.1 volts. Is that okay? But under non-standard condition, your concentration here is not 1 molar, and your concentration here is not 1 molar, and therefore your E naught cell is going to be different from your E cell. So this E cell now is what we can calculate using the Nernst equation. Is that okay? When also we have change in temperature, you can use the Nernst equation. When you have change in pressure, you can use the Nernst equation if your reactants are gaseous. So the value of electropotential, that is the E cell, will depend on the various concentrations that you have. And normally that effect, it has to do with the kind of reactant you have and the product you have. And you know that normally when you have equilibrium reactions, once you perturb at one end, it's going to affect the other ones based on the Le Chatelier's principle. So now this is the equation that we call Nernst equation. Your E cell, that is generally, and under standard condition, it is this. Then minus whatsoever you have here. No, you have used the log here, and now your equation based on assuming that you have equation going to C plus D, and the A and C, activity of D raised to power D, activity of A raised to power A, activity of B raised to power B, based on the earlier equation we used, that you have A small a capital A plus small b capital B to give you under equilibrium condition small c capital C plus small d capital D. So now that was why we wrote that equation we have, because your K here is going to be C raised to power C, D raised to power D, B raised to power B, over B raised to power B, A raised to power A. But mind you, I used, my internet is unstable. So mind you, I used activity, which is the right thing to actually use for such equation. Now, I want to show you how we came about Nernst equation itself. Normally, in thermodynamics, when you have delta G will be equals to delta G naught under standard condition plus RT link K. That is what you have normally under thermodynamics. So based on that, your delta G is equal to delta G naught. If you decide to use log, is going to be plus 2.303 RT ln K. And we know that delta G will be equal to minus NFE cell. Remember, this has not, this has no not. Delta G naught is going to be equal to minus NFE E naught cell. So instead of writing our delta G here and our delta G naught here, we can substitute with the various values we have. And that means that this is going to be equal to minus NFE cell equals to minus NFE naught cell plus the rest of the equation. Is that okay? So if you divide all through by NF, so this one remain E cell, and this one remain E naught cell, and the last one is just going to be this, because I divided by minus NF. This one will be minus 2.303 RT log K over NF. So I hope you can see how our next equation has actually come around. But you see, you can see concentration here. Your concentration is actually embedded in the value of K that you have here. It's embedded in the value of K that you have there. So if you open up your value of K, this is what you have using activity of C, activity of D, activity of A, activity of B. And normally in principle, when you have pure solid, you take it to be 1. Or when you have pure liquid, you take it to be 1. So in most cases, what you actually consider will be the aqueous forms of the various reactants that you have. So the same way you can, instead of A here, if you using partial, if you are using of the various component to give you the equilibrium constant. So now let's look at this example. If you are to calculate the EMF of this, the electromotive force of this, you have been given the cell notation. It is now left CO going to CO2 plus. And actually, your reduction potential is CO2 plus going to CO. Just that means you have to change this last one, and your N, your Ni going to Ni2 plus going to Ni. So that means you leave this one the way it is, and then you change the other one. Let's just go and see what we have from the equation. So this one, I said you will change, and because you are changing this, that means this one is going to become positive now. It's CO to CO2 plus 2 electrons instead of what you have here. And the other one, we just bring it down the way it is. So now, if you add up the two, you get this net equation. The same way you have added these two half reactions together, you have to add this together. And your E here, your E cell here, E naught cell here, because these are the standard conditions, is will be equals to 0.023 volts. This is E naught cell. Is that okay? So now you know your E naught cell. Now your N here is going to be what? You only have 2 electrons that will cancel that. So N is going to be equals to 2, and therefore you substitute into this equation. That E cell will be equals to E naught cell minus 2.303 RT over NF log. Now, this one is in aqueous form. This is in aqueous form. That is concentration of your cobalt ion over concentration of your nickel ion. So that is the equation. So if you now decide to go ahead to find the value of your E cell, this one we have determined 0.023 from here. And we substitute all the other values. Your cobalt is 0.1 as given in that equation, and your nickel is 1. You just substitute it, you substitute the values there, and your final answer is going to be this, and your answer is approximately 0.053 volts. So that is the E cell for this reaction. But the E naught cell for the reaction is actually 0.0234. So when I give you objective questions, I'll give you A, I'll give you the E cell. B, I'll give you the E naught cell. And what I actually want from you is E naught cell. But if I've given you all these other values, your thought may be that, okay, actually I was expecting that you calculate the E cell for me. But my question will probably have simply stated, calculate the E naught cell. So you have to read the questions very well before you go ahead and pick your answer. Okay, so we go on and look at another example. Look at this example for E cell for this reaction. So you go ahead and normally you'll be given the reduction potentials. This is this, and if you look at this, this is SN2 going to SN4. So SN2 going to SN4 is going to be opposite what you have been given here. Your silver plus going to silver is going to be the same thing as what you are given there. So we just bring it down, and when you find the net equation, you discover what you have is actually what you have in this equation. And now, look at this. We multiply this all through by 2 to be able to get 2 electrons. Is that okay? And the value here is not multiplied. Remember, I told you it's an intensive property. So we are not going to multiply your E naught cell. I said it earlier. I'm just repeating it again. So when you add this up, your equation will finally be this, and your E naught cell is this. Now you just go ahead now and substitute in next equation. Once you substitute in next equation, that will be, this is the aqueous form of the product, and the reactant, you have this and you have this. So remember, because this is 2, that means this one is going to be raised to power 2. The other ones are just 1. That's why they are the way they are. Now your n here is going to be what? What is your n? Because we multiply this one by 2, so your n is actually 2. So your n is 2. Your E naught cell is already calculated here, and your SN4 plus is already given in the equation, and your SN2 plus already given in the equation, and your AG plus is already given in the equation. So all you just have to do now is to go ahead and substitute into that equation which you have here, and then you get your final answer. So your silver is 1. So I think there's an error here. Your silver plus from that question is 1. So you can see it's 1. So there's an error here. This is actually 1. But the answer here is correct in that it is 1. So 1 squared. So when you solve this equation, your final answer is going to be 0.637 volts. So this is the way you use next equation. There are so many other examples. I'm not sure we can begin to go through all of them. But if you look at this example here, it said in the above equation, that equation we have just dealt with, what is the minimum silver plus at which the cell is able to function as photovoltaic cell with SN2 plus slash SN4 plus as anode. For it to function as photovoltaic cell, that means the minimum value of your E naught of your E cell must be 0. Of your E cell, the final E cell must be 0. So what you do is you go ahead now and try and calculate if you have to put your E cell to be equal to 0. So what you just have to come back to this equation. If this one must be 0, then you substitute the other values, and your AG plus here will be an unknown value because all these other ones you know. So now if this your AG plus is an unknown value and the E cell has to be 0, I think this one will make E cell not be here. E cell to be 0 because that is not the standard condition. Then what you have here, your AG plus, you just substitute the various values, and then you get the value for your Ag plus. Your Ag plus must be 1.731 times 10 raised to power minus 11. So for that reaction to be spontaneous, to be a photic cell, that means the concentration of your silver must be at least this. Anything less than this, that means that reaction will not happen. So you have to apply electricity to make that reaction happen if the concentration is below this. So that's another example. Now, the concentration of iron in a redox reaction can also be determined, can also be calculated using Nernst equation, just like any other parameters. If you don't have the iron before, you don't know what the concentration is, like here, our iron has been made to be X, then you just substitute into that equation like the previous ones. I won't be going through this because of time. You just substitute into the various equations like we had earlier. So instead of putting the value of your Fe plus here, you put your X here as the value of the concentration of X. And this value you have been given in the equation, and then the inner cell, so you just substitute into it, and then you get the value of your X. So these are examples that you can go through. Now we go to another part of our lecture after leaving the next equation, and that is concentration cells. Concentration cells are cells that what you have are the reactants, the same species you have at the reactant, and the same species you have at the product side. So that means the E naught of concentration cells will normally be equal to 0, because the same reactant you have at the reactant is also what you have at the product. So this is what we normally call concentration cell. And I said typically the E naught cell will be equal to 0, because your half oxidation reaction is going to be the opposite of your half reduction reaction. So when you combine, your answer will always be equal to 0. And a typical example of concentration cell is your pH. Your pH is a typical example of your concentration cell. So what normally is done is that your standard electrode, you have your hydrogen inside another solution. So your concentration of hydrogen in one is unknown and concentration in one is known. So based on that, your E naught cell is going to be equal to 0. Now you can calculate your E cell. So once you calculate your E cell, then you can calculate your pH. I will show you the relationship that you have between E cell and pH very soon. So we continue with concentration cells. This is an example. If you look at this, this is unknown, this is known. This is one half cell, this another half cell. They look alike. So the oxidation, you have H2 going to 2H plus 3 electron. Then the reduction, you have the same thing. So this, if you turn this the other way around, oxidation, that will still be 0. Is that okay? Minus 0 is still 0. So the net equation, the E naught cell, you add the 0, 0 here, it will still be the same thing. So you just go to your next equation. Your E cell will be equal to E naught cell minus, we said the standard condition, then that will now be multiplied by, when you look at this is X squared. Is that okay? Concentration of hydrogen here squared, and concentration of hydrogen here squared. 1. This one is 1 squared. So now, if that is 1 squared, and our N here is 2, because we have 2 hydrogen atoms involved. So now you can now go ahead. This is now like 2 log x. Log x squared is 2 log x. And then these 2 will cancel this. Is that okay? Your E naught cell is equal to 0. We have brought that one down. And from there, your E naught cell will apparently now be equal to minus is 0.592. There's 0 here that has been omitted. Is 0.592 log X, because these two has cancelled these two. So your E naught cell is equals to this. And you know that X is concentration of hydrogen. Is that okay? So minus log X, if you minus here, log X is the same thing as minus log hydrogen plus. Is that okay? And that is the same thing as pH. That means that your your E cell will actually be equal to this value multiplied by pH. That's an important equation. So under standard condition, your E cell is equals to 0.0592 of pH. So that's why it's possible that you have some pH meter, you can read out your E cell from that same pH meter, and you can read your pH from the same pH meter. So all you just need to do is program that calculation into it, then you can always get your answer. So we go on with so there are several examples of concentration cells, and another example is when you have silver electrode. So the silver electrode is not the most convenient electrode, because normally the standard hydrogen electrode is not the most convenient electrode, because normally when you have your standard hydrogen electrode, that means you have to be carrying your hydrogen gas about. You have to be bubbling hydrogen gas over your platinum electrode. That is not something that anybody can readily carry around. So because of that, we have some type of electrodes that we say that they are secondary electrode. Secondary electrode in the sense that they have been measured against hydrogen electrode, and because of that, you can now use them invariably to measure others, because they have a well-known electrode potential. So a sample of such is your silver electrode. And in this, the old potassium chloride solution with chloride ion concentration of 1 molar. So that is the normal condition, and this is the equation for your silver electrode. You have your silver in silver chloride, now in chlorine, and under 1 molar. So once, if you have measured that against hydrogen electrode, against standard hydrogen electrode, the value of your E cell is 0.022233 voltage at 25 degrees C. And that simply says that whatsoever you use this one to measure, you just have to make the allowance for the value of this to actually know what the exact value the other one will have. So this is the typical equation for this reaction, and the half equations are given here. That means you have hydrogen going from hydrogen gas to hydrogen plus, and the other half is your chloride. So you have your silver chloride now going to silver plus chloride minus, and you have this equation. So you have another type of electrode apart from the silver electrode we've talked about. You have calumet electrode. Once we talk about calumet, what comes to your mind? Once you hear calumet, what comes to your mind? So do you think of mercury? So normally in calumet electrode is another type of secondary electrode, and sometimes people say it's mercury electrode. Sometimes people say that. So in this case, you have mercury that is in contact with your mercury chloride. So they call it calumet, mercury chloride. So, and it's immersed in a solution of 0.1 molar potassium chloride. So that is what forms the cell of that, or just say have a saturated solution of potassium chloride. The EMF for this, the E cell for this, is 0.337 volt at 25 degrees C. So that means if you are using calumet electrode, all you have to do is just to make a difference for this thing. And this is the equation, the notation for that electrode. And then these are the half cells, and then the final equation is this. So the E cell for this is actually here. So let's take another example, which is the most common example. That is a glass electrode. That is the one you see all around. You want to take measure pH and the likes. That is the one we have. So it's the most convenient secondary standard electrode that is often used. And then if you have seen, well, I'll show you a picture of one that it has a hollow glass tube. And inside that hollow glass tube, you have a tiny glass membrane, that is round about it, that is carefully regulated. The composition of what you have inside compared to what you have at the bottom has to be carefully regulated. That now the tube is filled in part with solution of your hydrogen chloride solution, which is dipping into the solution of a silver wire that is coated with silver chloride. So you have that. Let me show you the diagram right away. Okay, well, you still have some explanations before the diagram. So the difference that you normally establish between what you have outside the membrane and what you have in the electrode that is deep into the solution is what actually normally gives you the pH of the solution that we are talking about. So it's like you have one half cell outside, one half cell inside, and these are concentration cells because you'll be considering hydrogen in what you have outside and hydrogen in what you have inside. This is okay. So a glass electrode is normally used with another reference electrode, normally which has a known combination, just like what we talked about earlier. And it must be one that will give you a galvanic cell. That means the E cell must be positive. And normally these days you just see the two inserted in a single one. So if you have a glass electrode, in many cases you see two tiny tubes inside it. One is the reference electrode, the one that is well known, and the other one will be that of the hydrogen. Then we have ion selective electrodes. Now the question is, we have this glass electrode, you can use it for hydrogen. Why do you still need ion selective electrode? Normally, instead of writing pH, you write px. X now representing the ion that you are checking on. When you are checking on hydrogen concentration, you have pH. When you are checking on chloride concentration, then it will be PCl. When you are checking on any other thing, it will be P that value. Now, ion selective electrodes will be necessary to measure whatsoever is the concentration of the various compound that you are looking at here. And examples of other ions you can look at will be sodium ion, potassium ion, calcium ion, calcium 2+, silver ion, ammonium ion. There are electrodes for measuring all this. And at the same time, you have for anions like fluoride, chloride, bromide, cyanide, and sulfide. So all these ones have electrodes. Then instead of you going to the lab, having to do the calculation, to start determining the concentration of each of these. Once you develop this type of electrode, all you just need to do is put it in the solution. You get the px of that solution, and from the px, you can get whatsoever your concentration is directly. So ordinary pH electrodes cannot be used to measure sodium ion and potassium ion. And I'm sure you know the reason why. The reason why is that the moment you put your sodium in water or you put your potassium in water, you are likely to have electrode. And the concept of concentration cell normally
Are we going to do it now?
Oh wow.
Please, I can't hear anything, please.
Me neither. I can't even hear anything at all.
Sir, it seems like you've muted your mic, sir. We can't hear anything and we can't see the slide.
You can't hear anything.
Sir, we can tell you.
Actually, I'm seeing last. Hello. Can you talk?
Not hearing anything, no.
You've not been hearing anything since, sir.
We are not having to modify about 20 minutes.
Like 10 minutes, sir. We couldn't hear
For the
you.
past 10 minutes now, it have been quiet.
I've not been hearing anything. You are just hearing you
Okay,
now.
that means on potentiometry.
Sir, I have a complaint.
Network is down.
What your complaint?
Hello.
What's wrong?
We can't see your voice, sir. We can't see your voice.
We can't hear your screen, sir.
We can't see your voice.
Sir, please, what's the difference between E-cell and E-not?
You are too fast.
We can't hear your
Slow
screen,
things
sir.
down a bit.
All these students in
You'll get out.
Sir, what's the difference between E-cell and E-not? E-not cell.
He said, and not. He said,
Hello, may you calm down now.
this is a standard condition.
Put it for house.
This is at 25 degrees Celsius.
Hear you. We can't hear you.
I just the lecturer,
Please, who is explaining E-not? Please, I'm listening.
Not is a standard condition at 25 degrees Celsius.
everybody.
That's the class ended. This is 12.
Just BMF of the cell.
So help me explain it on the chat room. Thank you.
Hello, I'm a bossy and I'm a guessy. Now you take see the lecture.
Please, who is that?
I do that as I completed that COP.
Hello, the class has ended now. Abi?
Log out now.
The class of you guys now. I mean, which kind of question that one?
Excuse me. Since you guys
Olawale Victor, show you there.
The man is very fast.
since you guys have data, Abi. Oh God. Olushola Shegun, you.
Just shut up, John. Leave the meeting.
Excuse me. Fuck you big time. Man, no point.
Before you do fuck you, just explain something to the picture.
Ṣẹ́gun, now no cash you for inside UL.
What you want to do?
Ẹ gbà mí.
Class don't end. Leave the class.
I wish you leave the class. You first.
Kí ló máa ń ṣe